All right, welcome everybody. So welcome to the first Zoom talk of the New York Group Series seminar this semester. So it's a pleasure to welcome our speaker, Laura Ciobanu from Heriot-Watt University in the UK, and she is going to tell us something about group equations, constraints, and decidability. Laura, please.
Yeah, thank you very much for the invitation. I'm very happy to talk, although it reminds me of the pandemic because I haven't done Zoom talks in a while. I will talk about two papers, one with Albert Garreta that I think everybody knows in New York, and the second paper is with Alex Evets and Alex Levine. So this is a very special crowd in New York that there's a lot of experts, but so I will maybe not do as much introduction as I normally would. But in any case, central to our stories is Hilbert's 10th problem. It's both an inspiration and a tool and sort of beginning, middle, and end of the story. So as I think everybody knows, the Hilbert's 10th problem was about, stated in the 1900s, about finding an algorithm to see if polynomials with integer coefficients have solutions, right? And that's my favorite picture of Hilbert with his great hat and the book where he published his famous problems. And as we all know by now, so this was a while back, this is an undecidable problem. There is no such algorithm to find the solutions of Diophantine polynomials, and this was Matiasevich plus, and the plus is many others contributed in various ways, in significant ways to this result. So as I said, inspired by this, but also using it as a tool, we're going to look at equations in groups and monoids. And yes, there will tend to be non-abelian. And just to get everybody happy with the notation, I will look at free groups to start with, and I'll write FG for free group. I will have at some point free monoids, and then I'm going to have FM. So this is just a notation, and say if I write FG on A and B, it's the free group on A and B. And an equation is, say, over this free group, means that I'm giving myself a set of variables, and I have them here in red, x, y, with their inverses, and so on. And this is a very nice equation that I think many of you know and like, that you can ask, for example, when is the commutator of x and y equal to the commutator of A and B, where A and B are the generators. Okay, so I won't say very much about this. This was just to say that's an equation, and a solution is a substitution. You say, okay, if I make x equal to AB and y equal to B, you plug them back into your equation such as this and expand, and you see after some cancellations, you get the commutator on the other side. So this is indeed a solution. And there are two natural questions. So the first one is deciding satisfiability. So what do I mean with that? Simply asking, does an equation in a group, so your favorite group, does it have solutions? Because this is a decision problem, the correct way to ask this is, does there exist an algorithm which for every equation can determine whether the equation is satisfiable, meaning it has a solution. And for the purpose of today, I won't give a big historical overview, but the purpose of today, it suffices to know that in free groups, a major result, we know that equations are, or rather are decidable, so we can decide satisfiability. The same holds for right-angled arcing groups and hyperbolic groups. There's other groups that we know things about, but I'm mostly going to mention these today. And the second question, which I won't say very much about, but if you have solutions, you might want to know what they look like. So describe them and in, say, rags, in hyperbolic groups, we have ways of producing the solutions. So these are the two basic questions. I said two natural questions. I think they've been called Diophantine problems in the literature. You can ask them for semi-groups, not just groups. And I will bring that in a bit later today. But so this is the classical setting. Now, what I'm interested in today is just add a layer of complexity to this. I want to look at constraints on the solutions. So I think constraints, I don't know, as a sort of pure mathematician, I'm always a bit dubious. When I hear constraints, I think of, I don't know, numerical analysis and PDEs with some constraints, but I learned to get over my my bias, my I don't know what is the right word, to accept constraints as a very good thing to look at. So what do I mean by Diophantine problems with constraints? I want to know, does some equation have a solution that belongs to a certain set? And that certain set is going to be my constraint. So a constraint is simply a set of a particular kind, quite explicitly given, as we'll see. And of course, we might want to also produce the solutions satisfying some constraint. Okay, so this is just basic, what I mean by constraint. And then now this is not a very precise classification, but I'll say that there are two main types of constraints, at least for today. Some that are, let's say, easier, not necessarily easy. And that's when I ask the solutions to some equation to belong to a regular or rational set. And regular, for those of you who know, and I'm afraid I'm not going to say very much about it, it's those recognized by finite deterministic automata and so in the language theoretic sense. So what is such a constraint? An example would be, are there solutions of even length? So if I have an equation on x and y, I want to know, is there a solution where for both x and y, somehow the substitutions, the words that are solutions are even? So this is something that is regular. What is something that is not regular? So I would call it harder. It's something that you can't just say belongs to a regular set. So if I ask, are there solutions to some equation where the length of your solution for x is the same as that for y, that is something that you cannot express in terms of regular languages. So I'm happy to say more about it later, but let's yeah, that would mean doing quite a lot of language theory, which I'm afraid we won't have quite the time today. But still, just to fix this a bit better. So what is regular versus rational? They are essentially the same if you're in free groups or in free monoids, but we are going to look at groups beyond the free ones. So if you have a group given by a generating set S and the usual projection from words to elements, then I will say that a set is rational. So a set of elements in my group is rational if it is the image of a regular set. So you have a regular set of words over the generating set. Is there, if you project it onto elements and you get the set L, then it means L is rational. And now, slightly different is a recognizable set. And there, what you do is you're looking, again, pick a set of elements, L, and you're looking at all the words that give you that set L. And so, in other words, the pre-image of L, and if that is regular, then you say L is recognizable. So in particular, it takes a minute to check that if you are recognizable, you are rational. All right, so I'm not going to say a whole lot about this, but so don't worry if you're not familiar with these concepts. Just every now and then in a fairly a limited way, I'll mention them. So I said easy. Again, this wasn't right. Probably I should, as I said, it is just easier than the non-rational ones, because this was still a lot of work. There's milestones about solving equations with all kinds of constraints, starting from the 90s, or well, this line of research started in computer science. So we had so when I say word equations, I mean in free monoids, and I'll come back to that. So there's a very successful and important line of research dealing with rational constraints, involving not just computer science results, but also, for example, hyperbolic groups. So there's a lot of work in this direction, but what I want to talk about today is non-rational constraints. So I already told you a bit that length, for example, will end up being non-rational, but just very quickly, so I'm going to talk about 3 kinds of rational constraints, and this is why I'm doing this basic definition. So the length of this is 5. And sorry, now this is not, let's just do this quickly. So I'm going to talk about length. I'm going to talk about the exponent sum of some generator, and I'm going to talk about the abelianization of the group and of an element. So I'm in a free group for now, right? So we can always talk about length in any group. That's not a problem. So this would be 5. The exponent sum, I think it's also very well known to everybody. You're looking at how many times a generator appears in a word. And here I have A. A appears once with +1, 1, -1. So that's going to be exponent sum 0. And finally, if you do the abelianization of a free group, you get z squared. And then here I have my element. What's the abelianization? Well, it should be, what is it? All the a's die out, and there's a b cubed. So what is it? Z 0, 3. So these are the 3 things I'm going to focus on. And I'm going to add these constraints to my equations. So what do I mean by that? Well, I have here an equation in the free group on A and B. And I want to ask, are there any solutions where the length of x is length of y plus 2? Okay. So this is what I mean by length constraints. And well, I chose a very easy equation, of course, where I could deal with this quickly. And turns out, yes, x equals b inverse a inverse, and y is the identity, will satisfy exactly that. Okay, so this is the kind of questions I'm going to ask. So this is one kind. Another kind is asking, so same equation, and I'm asking, is the exponent sum of a in x? So is there any solution such that the exponent sum of a in x is twice exponent sum of a in y plus exponent sum of b in y, and so on. So I'm just setting up some system of linear equations involving these exponent sums. And well, again, so what would you do here? This is an easy example. What I did was just, again, abelianize this, and then you think of how many a's are in x and in y squared, y inverse, and you set up some equation as a linear system, and you're not going to get solutions where the unknowns are exponent sum of a in x sorry, of a in x, of b in x, a in y, and b in y. So this is an ad hoc treatment. Nothing very deep yet. It's just to set up the problems. And the last question is, again, I have an equation. Are there any solutions? Well, let's say the abelianization of x is 3 times the abelianization of y. I'm talking about elements in z squared, so I can say 3 times something, right? And again, when you abelianize, you look carefully at everything commutes nicely. You get something like this constraint. So abelianization of x is 3 times abelianization of y, if and only, well, sorry, if that happens, then you get 4 times a pair of integers is -1, -1, which cannot happen because you're in z squared. So these were just some examples to see the kind of problems I'm looking at. So 3 types of constraints. The first one is the Diophantine problem. So this is why I have DP with linear length constraints. So I'm asking the lengths of solutions to satisfy a linear system of equations. The second problem is linear exponent sum constraints. So now I care about the exponent sums, that they have to satisfy some linear system of equations. And finally, the last one is about so abelian constraints or predicates. I don't know what the best way is to say it, but in any case, I'm asking that the images of the solutions in the abelianization of my group also satisfy a system. So 3 questions. There's somehow, well, there's reason why I have these 3 questions that I'll come to in a moment. But the first recap is that if you're looking at equations in free groups, free monoids, and free-like structures such as hyperbolic and so on, equations are decidable. But what I want, so classically by the work of that I mentioned before by many people, very important results. But what about equations with non-rational constraints? And as I said, I'm going to look in particular at these 3 types: with length, exponent sum, and abelianization constraints. So let's see what happens in free monoids and free groups. So as I said, if I write Fm now, we're in the free monoid as opposed to Fg, which was the free group. And there's a classical and much celebrated paper in computer science of Büchi and Sanger from '88. And the inspiration of our work, and which says that for word equations, meaning equations in the free monoid, the Diophantine problems with abelian and exponent sum constraints are undecidable. So as you recall, I had 3 questions, right? 3 types of Diophantine problems. One was with length, let's say G and L, G for group, L for the length. Second one was for the exponent sums. And the third one was abelianization. Of course, you can abelianize a monoid too, right? You just get some natural numbers at, a power of that. So what Büchi and Sanger noticed was that these last 2 questions, and now let's replace group by monoid, and it's really the free monoid. So problems, if you want, 2 and 3 are undecidable. And what do they do? Well, as I said, we're going to come back to Hilbert many times. They interpret the ring of integers into the free monoid, where you can multiply and solving equations in the free monoid, and you also are able to use exponent sums as information. And so as soon as you interpret the ring of integers, you have arithmetic and things become undecidable. And well, they sort of they don't state things quite this way, but they also, I think, more or less show that the problems 2 and 3, so with abelian and with exponent sum constraints, are equivalent, meaning if one is decidable, the other one is as well, or undecidable. And if they were decidable, then they would imply that question number 1 is decidable. Okay, so these were question, I guess this was 2, question 3, and this is question 1. The 3 kinds of Diophantine problems. But of course, since in this problem, in the theorem, they showed that questions 2 and 3 are undecidable, we're not going to get anything about question 1. Because here it says, if they are decidable, then we know something about question 1. Since they're not, we don't know anything about it. So, well, it turns out that that question 1, so solving word equations, so I'm really looking at free monoids now, with length constraints, is one of the biggest open questions in theoretical computer science. And it's been open since the 70s, and it's got all kinds of implications. And I recommend, there's recent surveys, well, maybe one not so recent, 2018, about the satisfiability of word equations with all kinds of constraints, and a very recent survey that's again, I'm gonna show you a bit about in a moment. So why is this problem so important? Well, first of all, at the theoretical level, if we prove that these are undecidable, it would be a sort of a new proof, an alternative to showing Hilbert-Stent problem, or to showing that the Diophantine polynomial are undecidable. And they also have practical importance because well, so I'm learning more and more. String solvers in all kinds of places are using these constraints. So string solvers essentially deal with solving word equations with various kinds of constraints. Sometimes your spaces may be finite, but you still need to know what is possible as your space becomes extremely large. So there's huge interest in the applied side of string solvers in this question. And as I said in this last survey, these are all the new string solvers that seem to pop up all the time, where they look at some sort of word equations with constraints. And in the same survey, there's a list of various constraints. So here, for example, let's see. So this is all about word equations, and here, this one, it's rational constraints. So it's asking, is X in L of R, where L is a regular language? Or you can ask, is your variable in a context-free grammar? Or you can ask, all kinds of lexicographic constraints, length, and so on. So these are things that people really have looked at and are interested in. And so it's just a list, and we picked some of them, the most sort of classical and also algebraic of all these constraints. Right, so Albert and I started to look at this, and we noticed that what they have done, so Büchi and Sanger did for free monoids, can be done for free groups. And I think the experts, if people have thought about it, this is not very hard to show. But we wrote it properly. I mean, the paper is from '88. It's written in a funny way. It's not that it's difficult, but it's I find the notation just not easygoing. So we put it in a language that is very precise, and I'll show you how we do that. And so we showed that again, same results. That this is problem 3 and problem 2. They're undecidable, and as before, they are equivalent, meaning that if you can solve question 2, you can solve question 3. So how do we do this? So let's see how we encode the ring of integers into all of this. Well, we took their results that were written in a kind of funny way, and sort of combinatorics on words, and interpreting that in a not so clear way, and just put it in the language of model theory and interpretability. Again, I think familiar to lots of people in Europe, but so the idea is, right, to interpret the structure. So you have G and H. They could be groups, rings, fields, whatever you like to, and you interpret one into the other means in terms of first order logic. So everything about H, say, you can read it from G. So what do I mean by everything? Well, you would like the set H to be definable in terms of G. You would like to have the set so you like to say when two elements are equal. So, right, so sort of H1, H2 with H1 equals H2, you would like that set to be definable. If you have sums, you would like triples like H1, H2, and H1 plus H2 to be definable. If you have products, you want that to be, and so on and so forth. So via first order sentences. So now I could have given the very full, heavy definition of interpretability, but I think this is more helpful. But I need to make two comments here. First of all, we're not using the full power of first order theory to define these things. We just use systems of equations. So we use something that we call interpretability. So what we mean by that, P is for positive existential formula or simply systems or disjunctions, so unions, let's say, of systems of equations. So we define sets. We don't need, as I said, it's just existential sentences. There exist tuples that are the solutions of some systems. So we use that. And another comment that I want to make is often we want to say H together with some relation. So some added power to your structure. We want that to be PE, say, interpretable in G with some other. So let's say RH here and RG. So for example, length, if we want to talk about the length of two elements being the same in H, if we have that power, we want to translate that or be able to express it in terms of G with some other relation. So we're modifying a bit the very standard interpretability, but everything that you know should hold and holds. And so the usual, right? So I said I want to define various things about H in G. So definable sets. One typically defines them in terms of first order formulas. And for today, you just need to know things like a centralizer is definable because, well, you can express, right, in terms of equations. And that's the thing. I want not the full power of first order theory, just PE definable, just the sets that can be given by solutions to equations. So a centralizer is such a solution, is the set of solutions to this equation. And because of that, then, for example, any cyclic subgroup, and I should say, no, the cyclic subgroup, not every cyclic, but here I mean exactly this guy generated by A, that is definable because we know we can define it as a centralizer of A, right? So these are examples that I will need for later. And as I said, I can actually define them by equations. I don't need more than that. And that's what we're going to work with. So let's see what I mean with all of this, because yes, it can get heavy, but I don't want it to. So I want to remember I had this lemma which said the Diophantine problem with exponent sum constraints, so we are in the free group, okay, is the same essentially as the Diophantine problem with the abelian constraints. So question 3 and question 2. So I want to be able to go between the two via, right, this little bit of interpretability. So so as you see, it's solving equations where you are able to also say when two things have same exponent constraint, and you want to say that's the same as solving equations where you are able to say that two things have the same abelian image, for example. So how do you see that? Well, let's say we're in this free group, and I forgot the G here. Well, it's clear that you can determine the abelianization of an element by just knowing the exponent sums of each of the generators, right? So if this is your element G, then the abelianization is, of course, really given by looking at the exponent sums of x1 and x2, right? So you can immediately get abelianization from knowing exponent sums. Okay, so one direction is quite easy. The other one you need to do a bit more, but I hope that by seeing that you you get a feeling by of what I meant with the PE interpretability. So so I want to see how can I get equality of exponent sums. So how can I say the exponent sum of some generator, here I have xi, is the same in G and H. If I know things about how to solve equations, and I know I can use abilization of elements in this whole story. So turns out, okay, this is a bit of a mouthful, but what I'm going to look at, so I have G and H. I want to know if the exponent sum of xi is the same. And I'm going to essentially say, well, it is the same if you can write G as, what do I have? WG prime, and if you can write H as WH prime, where G prime and H prime have exponent sum of xi 0, okay, here. And W appears in both places, and it's some power of xi. Okay, so it's not exactly, sorry, it's not writing that G is equal to that is the abilization of G, is the abilization of WG prime, and the abilization of H is the abilization of WH prime. So I need to stick an A, B here and everywhere else, but you see that the point of this is that if I can write things, equalities between abilization of elements, and if I can define the set xi to all powers k, then I am able and say when elements have exponent sum 0, then I can define this equality of exponents, so exponent sums. So let's see this again. So again, I'm trying to look at when the exponent sum of xi in G is the same, of xi is the same in G and in H, and I express it in terms of two things, in terms of abilization, where W is a power of xi, and these G prime and H prime have exponent sum 0, like that. So this bit here, can we interpret that in terms of equations? Well, yes, this is exactly, it can be given in a free group. It's exactly the W's, those elements that commute to xi. It's just very nice in free groups. And can we say that an element G prime has exponent sum 0 in a free group in terms of, again, equations? And yes, we can. If we think about it, it's the same as G prime is, or rather, how do we find some G prime with that property? Well, if you can write it in the product of all these subgroups, where you see they're the subgroups generated by x1, x2, and so on, except for the xi, because I want to have exponent sum 0. And each of these are definable, P definable. So so just at least as much my tongue is twisting in saying exponent sums and back and forth and abilization, but at least I wanted to convey that you can go between these two problems by expressing some constraints in terms of others, back and forth, and you don't need to use a whole lot. You can express the right sets in terms of equations. All right, so this is right, so what is the time? Okay, so I'm going very slow, so maybe I won't tell you much more about the free groups, but to go back, so what we have showed was that, so the Diophantine problem with exponent sum constraints is undecidable, okay? And I wanted to, again, prove that to you a bit more slowly, but what we do is we interpret the ring of integers into the free group with exponent sum. So what do you need to do to interpret that? Well, you need to interpret the integers as a set. That's very easy. You can always find a z in your free group. To define the sum is not too bad either. And to define multiplication is the one that's a bit trickier, right? So you need to find, you need to essentially, right? So you need triples T1, T2, T3, such that T1, T2 is T3 in Z. You need to find that in your free group using equations and using exponent sums. And if I have time at the end, I'll show you, but I don't expect I will. But since we interpreted the ring of integers using equations and exponent sums, it means we get undecidability by Hilbert's 10th problem. And that's why I said we use it as a tool in lots of these results. So this was the beginning about free groups. And yeah, I thought somehow this would go faster, but how do we move on to other groups? Well, first of all, yeah, my second recap, still staying with free groups, is that problems 2 and 3, you see, are undecidable. And because they're undecidable, we don't know about problem 1. So that the length constraints is this famous problem for free monoids. It's I think there's things to be done in free groups as things I'm thinking about, but for now we don't know. And so we moved on to other groups and tried to see what ideas can we keep. And when you move to other groups, length still makes sense, right? In any group, abilization of elements still makes sense. But you have to be a lot more careful with exponent sums. I mean, take a generator in a group. What is the exponent sum of that in an element G? Well, you have to be careful. It might not be well defined, right? So here I have a little example. If X has order 5 in a group, then what is the exponent sum of X cubed? Of X in X cubed? Is it 3? Or because X cubed is X to the minus 2, should that be minus 2? Should it be 2, right? So we have, as you've seen for free groups, we used a lot the connection between these two problems. So again, the idea would be to keep using it, but then you need to know what an exponent sum even is. So then we had to be a bit careful and define those generators for which it makes sense to talk about exponent sums. So if you take a group G and the abilization is infinite, it means you can write it like that, right? As a Z times some other abelian group, and A might be finite or infinite. And so what we're going to do is look at those elements. So I think it's here S, those generators rather, such that their abilization generates this Z guy or some Z in the abilization. And we called such elements, such generators, abelian primitive because they're primitive in the sense of generating Z, as we call primitive elements in a free group the generators, right? And abelian because they should be generating the Z, and that's in the abilization. So of course, all generators of a free group are abelian primitive. Also, any any group element corresponding to a vertex. So I guess I meant, yeah, the generators in RAGs, the standard generators, they are primitive, abelian primitive. They, right, clearly they will generate Zs and abilization. And then, well, you need to write down a few lemmas to make sure this is well defined. But if S is, as I said before, then the exponent sum of S in any element G makes sense, is well defined, and it's actually the exponent of the abilization of that generator in the abilization of your element G. So just you need to be careful, but it can be done. So that is part 1 of just being careful with the exponent sums. Part 2, and which I didn't have time to get into, But when I was trying to find multiplication of integers in my free group, what I did, which I skipped, what I had to play with two elements, S1 and S2, that were primitive or generators in F before. And that was really important so that I can encode integer multiplication, right? So I want to encode Z plus times the ring. So again, moving on from free groups to other groups, we do need two such elements to play with to encode integer multiplication. So long story short, we do need a Z squared in the optimization of our group to have enough room to encode integer multiplication. And so a first restriction, not a huge restriction, but to play the game, to do the P interpretability, we need the optimization of the group to be just big enough. And so once you have this, you have your abelian primitive elements, you have at least two of them, then we have our main results. And the first one is that if you have a RAG, of course, not abelian, then the question number 3, I guess, the solving equations with abelian constraints is undecidable. And the next result is for hyperbolic groups. Again, if the abelianization is just big enough, you can find a Z squared in there, then the problem is undecidable. So these are the two, the sort of the most technical results, and yeah, they're for groups with big abelianization. So see how much time I have to say about them. What do we need to prove these results? Well, of course, the ideas come from free groups, but it gets a lot more technical. So first of all, we need two abelian primitive, or just think of them as two generators that behave well in the group. Then we need to say, remember when I was playing the game with abelian, we were looking for things like G prime, and the exponent sum is 0. I wanted to define elements like that. Well, I need to be able to define that in my group. So I need things like RS is all the G's with the exponent sum of S0. I need to be able to say that. And these are the kind of relations that I mentioned before when I said the group with some relation needs to be interpreted in another group, or not necessarily group, the ring. And so, and then again, you saw briefly, I need to be able to interpret powers of an element, or in other words, the subgroup generated by S. I need to, and that was easy in a free group, something like that is just a centralizer, so it is defined by equations. But then when you move on to a RAG, the centralizer of an element is not so nice anymore, so it can be quite big. And so how do you define a set like that? And then it's not just a centralizer of S. And then in a hyperbolic group, again, how do you get a set like that? The centralizer is not exactly that. It might be virtually Z, and so you need to extract from that just the powers of S. So all of these can be done with a lot of work and some other technical conditions. And we played the game of, again, encoding the integers into equations with abelian constraints in these groups. And so I said plus other technical conditions. So yeah, the point is that yeah, we took the ideas from Büchi and Sanger, we formalized them and we generalized them using, as I said, this interpretability by equations. And that's how you reduce a problem to another. And this is the scary lemma where it's sort of, we need all kinds of relations about exponent sums and so on. If you have these things happening in your group, then you can prove the two big results or the main two results we have. And now I think I have maybe about 10 minutes. So it seemed like everything is undecidable. and all the results are negative. But then we realized, oh, something funny happens when you have your abilization of your group finite. So, for example, so take a group G where you can solve equations. So just the Diophantine problem in G, you can solve things. So that would be a hyperbolic group. That would be, well, a graph product of finite groups, such as a right-angle Coxeter group. So if in these cases, so finite abilization, of course, the right-angle Coxeter group also has a finite abilization. And in these cases, strangely enough, solving question number 3 is decidable. And again, I was planning to write more on this, but the reason why this is decidable is because we can, turns out that let's say something like abilization of X is abilization of Y. That's the same. You can always move things as abilization of XY is Y inverse, I guess, is 0. I don't know, I'm choosing, I guess, something of rank 2. And so what you're saying is that Y inverse is in the commutator subgroup of your group, but that commutator subgroup is a finite index because the abilization is finite. And that's exactly a recognizable set. So there's a nice result saying exactly recognizable sets are unions of finite index subgroups in groups. So turns out that you can boil down this question to Diophantine problem with recognizable constraints. And the surprising thing is, I mean, so people have asked me, well, so it seems like, okay, in free groups, you cannot solve equations with these constraints, with abilization constraints. But moving up, there might be a virtually free group, like the product of two finite groups, where you can solve. So it doesn't mean that if you have a free group in your group, you're suddenly stuck. It does matter how the abilization behaves. So which I find very nice and interesting. Right, so these are a few examples. Just to recap everything. So this is a graph product, right? That's my graph product. Everything is finite order, all the generators. The abilization is finite. So I can solve, by the previous slide, I can solve this question number 3. But in a RAG like this, where the abilization is very big, I cannot solve it by the negative result. Sorry, that's an AB here. I cannot do it. Okay, so the abilization plays a big role. And finally, if you want to look at hyperbolic groups, this is a free product of a bunch of finite groups. The abilization is finite, and because of that, I can solve question number 3. But if you're looking at a surface group where, of course, the group is hyperbolic, the abilization is big, then again, you cannot solve the question, or it's undecidable. So there's a sort of nice, interesting thing going on. And how do you put all of this together? So where are we with all these questions? So this was question number 3. This is question number 1. There's not much to say here. As you see, there's just question marks. But so as a summary, for hyperbolic groups with big abilization, big L2 Betty number, we showed it's undecidable. The question number 3. What else? For RAGs, it's undecidable if they're non-abelian. For right-angle Coxeter groups, because the abilization is finite, is decidable. Here again, abilization finite is decidable. And what we don't know what to do is when the abilization has rank 1, or rather free rank 1. Right, when the abilization of your group is Z, say, we don't have enough room to play with, enough generators to get our multiplication. So I'm very curious about what happens there. Or for example, just the braid group on 2 strands. The abilization of this is what is Z, right? And again, we can solve equations in B3, but Z is too small. We don't have 2 independent elements to play with to get results. So these are things that I'm very curious about, but don't quite know what to do. And at the very end, I guess I have maybe 5 more minutes. So a lot of, right, so mostly negative results, so things being undecidable. And after Albert and I wrote the paper, I talked to my former students, Alex Evets and Alex Evin, and we looked at virtual abelian groups where things tend to be nice. And they are even nicer than I thought. And then we were very happy with these results. So these were the questions. Okay, so this was question number 3, and this is the big one about length. Turns out things are decidable in virtually abelian groups. And also, if you even ask for context-free constraints, so you asking, is there a solution belonging to this particular context-free set, then this is decidable. And the reason why these things are decidable, so this is our result. So in any finitely generated virtual abelian group, it is effectively decidable whether a finite system of equations with all these constraints has solutions. So linear length constraints, abelianization, context-free, lexicographic order. So you're asking, is there a solution where x is smaller than y? Lex. So all these things that are not regular sets, typically, if you just write them in a free group or in a free monoid, that they're not regular, turned out to be actually rational in virtual abelian groups, which is very nice, I think. And well, that might not be surprising, but what we had to do in the paper wasn't just to show all of these turned out to be rational sets. We had to say what rational sets. We had to say, this is the regular image that, they're the image of this particular regular language. Because if you just know the constraint is somewhere floating in the air being rational, but you cannot give it, then you don't have an input to your problem, right? So we were able to really say these length constraints. So the set, say, in a virtual abelian group, the set of all GH, say, where the length of G is twice the length of H plus 1 or something like that, that is actually a rational set. And we can give the rational expression for it. And that actually, so this part 1 actually takes quite a bit of work. It's for those of you who know, I mean, a bit about growth. So virtual abelian groups have rational growth with respect to any generating set. And this is a work of Benson from the 80s. So it's great that you have a rational series, but Benson doesn't say how to construct that series. Is there even an algorithm? And what we did here is we did provide an algorithm, not just for that series, but for any such set where you have some length constraints. So this is why it's not just, yes, these things turn out to be rational sets, but we say what structure is. So something positive for virtual abelian groups. And yeah, these were the 2 problems, 2 references. So this was a pandemic paper with Albert, and this is a recent preprint with Alex and Alex. And yeah, I think that's it for me. Thank you.
All right. Thank you very much, Laura. Thank you.
Thanks.
Okay, so if there are any questions for the speaker, so you're welcome to unmute yourselves and ask them. Yes, Susan?
So when you look at when you say the length of X is equal to the length of Y isn't rational because a finite state automaton can't be checking this, that is true, but on the other hand, the set of all pairs of words where the length of X is the length of Y is a rational set. I'm wondering if there's any way to leverage looking at when the sets of pairs of things are rational.
But so in a free group, you don't have, if you, I mean, yeah, okay, depends how you write it, but so for example, I don't know, to start with the exponent sum. So if you want all the words where exponent sum of A is exponent sum of B, that is not regular, right? Not even context free, not anything. And also, yeah, I mean, abelianization as well, all the words or the sets W, U, where the abelianization of W is abelianization of U. Again, these are not rational, they're not regular in a free group and not rational in other groups in general. But they do happen to be rational in virtual Abelian groups. So this is what I mean non-rational constraints, because I mean, yes, they turn out to be rational in virtual Abelian groups because virtual Abelian groups are very special. So here it's sort of wrong to call them that way, but so even a context-free set in a virtual Abelian group is actually rational, which I didn't know before writing this paper. So it was surprising. But in general, of course, it's not going to be in other groups. So.
Laura, is it not just Parek's theorem that
Yeah.
a context-free subset of a virtual Abelian group is rational?
I mean, I wouldn't say. I mean, it's definitely follows from
I mean,
that.
and then you have a GSM which translates when it's a virtual.
Exactly. Yeah. Exactly.
So it seems that to me, if you know Parek's theorem, it seems clear. The lengthing is different
I mean,
because you're not using context-free language, but for context-free language, it's just Parek's theorem and GSMs.
Yeah. So no, the context-free is not the one where we had to work hard. I mean, it's just it's the length constraints. The context-free was just surprising to me because I didn't think of it before. And yes, I agree. If you know a couple of results, then it follows quickly. But I think, was it one of your papers, or I don't know, there was
Me and
something
Marcus use it on
transducers or
quite
something.
a bit. Yeah, transductions do finite index, and context-free is we use a lot with Marcus to do the rational subsets and graph products and stuff. Because the Parek's theorem is really, I mean, sort of very key for this kind of stuff.
Yeah, so
But
I guess,
I mean, if you know the result, it's obvious, and if you don't know Parek's theorem is not completely obvious if somebody doesn't tell you.
No, so I guess the point is here, once you have rational constraints, then you can solve equations with rational constraints in virtual Abelian groups. That's quite well, it's sort of a folklore, but yeah.
It's integer programming.
Well, anyway, yeah, so that's yeah. It's again, virtual Abelian groups are special, but still it's nice to have pretty much everything to be rational there. But yeah, for
the linear length doesn't seem clearly to me a context-free thing, but the other ones are, I think, in the Abelianization, but that's not virtual Abelian is not that big a jump either. Anyway, it's interesting.
So Laura, I actually had a question regarding exponent sums. One can define this condition with the exponent sums to a non-sign condition. So instead of the exponent sum on A, you look, let's say, at the number of occurrences where A occurs positively or negatively, or actually you can add them up instead of subtracting. So. And do you get something very different? Can you say anything about those things? Do they behave very differently? If you look at those refined quantities, so.
So we haven't really looked at them. In computer science, there's lots of people have looked at all kinds of problems around it on occurrences of letters
Yeah, right. That's why
in
I'm
all
asking.
kinds of ways. We haven't looked at them for free groups. I expect that things will be undecidable, playing it correctly, but yeah, we haven't really.
Okay.
But yeah, and again, in computer science, they look a lot of occurrences of A, occurrences of B, occurrences of A before occurrences of B. I mean, all the things that algebraically don't make a lot of sense, but they are of interest, and people have looked at them. So.
Okay. All right. Any other questions? Okay. Well, let's thank Laura again. Thank you. That was very interesting.
Thank you, Laura.
I'll stop.